First and foremost, what is thin film interference? Where and why does it exist? Generally speaking, thin film interference is an optical phenomenon that occurs when light reflects from a medium, for example, the coating of a CD or the membranes of a soap bubble. The result is a separation of different wavelengths of light in the visible light spectrum. In other words, joyous color-colored light is formed. Actually, thin film interference is a combination of two different things. The first being the condition that the medium is sufficiently thin. Why it needs to be thin will be explained later on. The second is another phenomenon that occurs when waves interact or interfere with each other, which is called interference, or in this particular case, optical interference. To understand thin film interference, interference must first be explained.
First of all, this is a wave of light. It has the amplitude of 1, and the amplitude defines the intensity of the light, how bright it shines. And it also has a set wavelength, that is, it's a certain color. Now, here's another wave that looks identical to the former wave. It has the same amplitude and the same wavelength, so it's the same color and shines just as bright as the other wave. Now, if these identical waves interact with each other, they will merge into one wave, whose amplitude is the sum of the former two waves' amplitudes, 1 plus 1, which will equal 2 and minus 2. This means this wave shines brighter than the former two waves, but is still the same color as it has the same wavelength. And this is called constructive interference. That is, when two waves are in phase, and when they interfere with each other, they result in a wave that has a higher amplitude than former waves. This particular example is a case of maximally constructive interference. That is, these two waves are perfectly in phase, so that the resulting wave has the maximum amplitude possible. However, if one of the waves is displaced by half a wavelength to the right, that is, half a wavelength to the right, and it will start here. And if it still has the same amplitude and still has the same wavelength, the sum of the two waves' amplitudes will become 0 if they interact. And this will result in a wave that looks like this, 0 amplitude. That is, the light will become will not shine. And this is called destructive interference. And this particular example is a case of maximally destructive interference. That is, the two waves are perfectly out of phase. They are perfectly displaced in relation to each other, so that the resulting wave becomes 0 light. The brightness is 0.
Therefore, some kind of condition is required to accomplish this displacement. This is where thin film interference becomes relevant. Imagine this red light as a single wave of purely red light. There's only one wavelength. As it hits the surface of the glass, it splits into two waves with the same wavelength. One wavelength is reflected off the glass surface, while the other is transmitted through it. This second wave is subsequently split into two waves as it hits the glass surface on the other end of the medium, while also being transmitted through. It is how these two reflected lights interfere with each other that is the phenomenon we call thin film interference.
For simplicity's sake, assume this incident light wave is angled perpendicularly to the medium surface. That is, it's actually traveling like so. But for simplicity's sake, by this assumption, this distance will be equal to the medium's thickness. And what relevance does this have to interference? Well, first of all, there is a difference in distance the transmitted and the reflected wave have traveled. And consequently, the transmitted wave will have traveled through the medium 2 times. And before returning to the initial entry point, the transmitted wave has traveled 2 medium thicknesses longer than the reflected wave. So the transmitted wave has traveled this distance, while the reflected wave has merely traveled this distance. And now remember the importance of interference that we explained earlier. Since these 2 waves are in the same space, they will interfere with each other, and as they are of the same wavelength, the same color, both are red, they will interfere with each other and form a new wave. And either it will be a destructive or a constructive interference, depending on the thickness of the medium, as the thickness defines the transmitted wave's displacement in relation to the reflected wave. And if the medium is as thick as 1 wavelength of red light, the reflecting light will be disrupted, and thus forming a destructive interference.
Although, if the light consists of all wavelengths of the whole spectrum of visible light, normal white light that is, which in most cases it does, it will reflect most wavelengths except red. This is because the medium's thickness must be directly correlated to a specific wavelength. This is why the medium must be thin, nano-thin. If it is too thick, like for example a window, a multitude of wavelengths across the whole light spectrum will be having maximum constructive interference at the same time, which only leads to the reflection of white light. However, if the medium is the membrane of a soap bubble, for example, which is nano-thin, only a specific color will achieve constructive interference, leading to a specific color being reflected. Why a soap bubble reflects different colors simultaneously is because its membrane's thickness varies, thus leading to different colors reflected at different places of the membrane. This is in contrast to the glass medium used, for example, earlier, which will only reflect 1 color. Conclusively, thin film interference can be found in many everyday situations. Hopefully, this explanatory video has brought some insight to the fascinating world of physics.